I'm Peter Sarnak from the School of Math. I'll take over from Jay. This is the third session of this special day celebrating Andy Ogg's, some of his contributions to mathematics and very generous gift to the Institute. So let's get on with it. As you heard in the last two lectures, he had a great impact in the theory of numbers and its connection to modular forms. But the theory of modular forms seems to have quite a far reach, and some of the more unusual reaches are something that Andrew impacted. And the next lecturer, Duncan, from Emory University and from Academia Sinica, will explain to us some of the ideas that go into what you heard David Nuremberg. Explain in quite some detail, and that's A Guide to Moonshine.
Okay, thank you very much. So it's a great honor to have this opportunity. So that, as Peter said, the title of the talk is A Guide to Moonshine. So there are two nouns in the title. One of them is present in the audience, so I will explain the second one. So the story of moonshine, the story of mathematical moonshine does involve alcohol, as has been hinted already. And it is illicit in a certain sense. And it begins at the Collège de France on the 14th of January, 1975, with the inaugural lecture of Jacques Tietz. So at this talk, the speaker describes some recent exciting developments in group theory. And in particular, evidence in support of the existence of a new final simple group that, if it existed, would be not of one of the expected types. So this conjectural group was at this point called the monster. And part of its significance is its imposing size. So the speaker wrote the order down precisely as follows: 2 to the 46, 3 to the 20, times 5 to the 9, times 7 to the 6, times 11 squared, times 13 cubed, 17, 19, 23, 29, 31, 41, 47, 59, 71. So this works out to be about 8 times 10 to the 53. So this is the point at which moonshine begins. Because the fates had decreed that our guide would be present in the audience that day. And he came equipped with an alternative point of view. So in particular, Professor Ogg had just answered a question for which this set of primes occurring in this prime factorization is exactly the set of primes of note. So to explain this question, so recall that E, an elliptic curve of a K, is called, well, I'll give the definition I like, which is super singular. Call it super singular if its endomorphism group is as large as possible. Endomorphism group of intervals and rings, sorry, of E over an algebraic closure is maximal 4. So recall that supersingular elliptic curves only occur in positive characteristic. Greater than 0. And it turns out, well, given just that, we can ask the following question, for which primes P, is it the case that the J invariant of every supersingular elliptic curve in characteristic P lie in the prime field? Turns out if it doesn't lie in FP, or it has to lie in FP squared. So but we can ask if there are any primes such that it always lies in the primes of field F sub P. And well, the answer reformulated in light of this factorization up here is the following. P, such P are exactly the P dividing the order of the monster. Primes P are exactly those that divide okay, so I'm going to jump ahead in terms of the history now and explain the kind of one of the main morals of this observation. So it's the following thing, which is a bit surprising from the point of view of finite group theory. The monster group is most naturally represented, if you like, the thing that deserves to be called the defining representation of the monster is not finite dimensional. Module call it the natural or natural. By the way, the existence of the monster was established here at the Institute, and is maybe would not have been established without the Institute. 79 into 1980 by Bob Grice. So this infinite dimensional module, its dimension, so to speak, or rather greater dimension, given by the normalized elliptic modular invariant, which is the J function, which I mean the J invariant for complex elliptic curves with the constant term subtracted, the usual constant term subtracted. Oh, yeah. Oh, that was.
En nooit met waar ze nemen techniek op fiets. 1984 of Orwell book comes from 1968.
Yeah. Yeah, I mean, the other way to remember it is 1 plus 47 times 51 times 79, of course.
Probably if you weren't born in 1958, it means nothing to you.
Oh, well. Exactly. I was a little bit later. So, and here Q is e to the 2 by 8 tau, as usual. Okay, so the monster is most naturally represented in some infinite dimensional space, and the greater dimension of that space is given by the J invariant. And Ogg's observation is telling us how to compute traces of prime order elements in the monster. Okay. So to explain that, introduce a little bit of notation. So gamma naught M, of course, has been mentioned. This is matrices like so with entries. I'm going to also use, for n an exact divisor of M, I'm going to consider extension of gamma naught M by corresponding Eckelmann evolution. So this is gamma naught M union matrices of the form AN, B, C, M, D, N. Now AD N minus BC M over N equals 1. And well, this explains what exact divisor means. So X sub gamma will be the compactified orbit space for gamma subgroup of SL through R. And X sub gamma M plus N. So rather than writing that, I'll write X naught M plus N and so on. So if we examine Ogg's method, then we can reformulate Ogg's observation a little bit differently. So observation prime. So P divides the order of the monster, but only a X naught P plus P is a sphere. Has no holes, i.e. it has genus 0. Okay. So the important point about genus 0 curves is that well, the first example is X naught 1, which is just the usual compactified curve attached to the modular group. Well, the J function, or equally the normalized elliptic modular invariant, this serves as a witness to the fact that this has genus 0, and for any other genus 0 curve, this has genus 0, say, then there exists a uniquely determined counterpart to the J function. It's a unique gamma naught n plus n invariant function. Let's call it J, so n plus n, the other half plane, that induces, descends to an isomorphism and it serves as a witness to that statement. Okay.
Up to a constant, right?
Sorry.
I have a question. At this point in the history, the monster was not known to exist, but the group theorists knew everything about it, including the complete character table. I've never understood how in the world they could do that. If he was here, we was here when he was constructing it. People here must understand that. It's a bit of mystery to me, and it's still there.
Yeah. So I think, I think so for me, it's also a mystery, but I'll pretend for a second that it's not, and I'll say, the character table of a finite group has so many linear restrictions. There's so many things that have to, come together for a matrix to serve as the character table of some group. And then, when you pair that together with the all the very rigid subgroup structure. Yeah. So for example, this 47 times, so this 196,884 is 1 plus the minimal, kind of what turns out to be the dimension of a minimal faithful irreducible representation. And you know that whatever that dimension is, it has to be a product of, it has to divide the order of the group, and then that by hypothesis you have these other groups that exist sitting inside there in certain ways. And so yeah, it's you can constrain the problem, but it still feels like a miracle. Oh, sure. Constant term? No? Okay. So I
would just think that up to a constant, right?
So it's unique.
Up to a constant.
Unique such that, well, it's unique up to where you put the pole and the constant. So I fix both.
Okay.
So I fix both choices. And so I make a q to the -1 plus 0, but something times q. Yeah. And I guess I'm assuming that the stabilizer of infinity is just translation by integers in order to have such a Q expansion. But that's the case for all these. For every group, I put it in the plot so far. Yeah. Okay. So right, so the miracle is, and here's the illicit part. So for each prime dividing order of the monster, there exists an order P element of monster such that the graded trace, say, trace T1 natural is exactly this function uniquely determined by P plus B. This level P analog of the J function. And why do I say it's illicit? Well, surely it's against the law that you should be able to compute the trace of an element of the monster on this infinite dimensional module without knowing anything about the monster. So well, so the so famously, Professor Ogg offered a bottle of Jack Daniels for an explanation of the coincidence, and I think well, I think half the bottle was earned. so let me explain what I mean. So Conway and Norton I assume with kind of help from Thomson, ran with this idea that the trace function, that there should exist a module and its trace functions should be principal moduli, should be analogs of the J function for any other genus zero groups. And they specify the kind of graded trace functions They gave predictions for these graded trace functions for all G in the monster. And then sprinkle Palsky and Merman, honored to have Lipowski in the audience today, came out, gave a Lie algebra-based explicit construction of a module of the monster of the natural. Reconstructed. And at this point, in the interesting situation where many of Conway and Norton's predictions could be confirmed, but not all, given the nature of this construction. So,
So were people looking for that module before there was that construction?
yes.
Yes.
Yeah. I think there was a lot of, yes. I think there was a kind of a, it was a race. Yeah. Professor Lipowski will be able to say more about that. Yeah. So Orchards came up with a stunning and beautiful marriage of algebra and number theory that reduced the otherwise impossible task of comparing Conway and Norton with Frenkel, Lipowski, Merman to an easy finite check. It was an easy kind of by hand computation. So so let me just say and it turns out that the construction of FLM agrees with the predictions of Conway and Norton. Confirmed that Conway and Norton, sorry, and agree, and his solution to this problem gave rise to whole new fields such as generalized Kac-Moody algebras. And I think inspired his theta lift and so on. So and well, as far as Jack Daniels is concerned, so this proof in particular, I think this explains half of Ogg's observation, half of the coincidence, so namely, it explains why if P divides the order of the monster, then X naught P plus P has to have G to 0. Explains why if a prime occurs in the prime decomposition of the order of the monster, then the corresponding curve has to be genus 0, but it doesn't explain the other half. So in other words, we still don't know how to get from an X naught P plus P that happens to have genus 0 to a symmetry of V natural, to an automorphism of V natural. That still feels like it's a long way off. Okay, so so there are three parts to this talk. In theory. The first part is monstrous moonshine. And we've just completed it. Next part concerns Umbral moonshine. Then hopefully there'll be time to say something about Torsion again. So
like where in this story was the monster actually constructed? I mean, in this whole thing of constructing the module,
yeah.
where do you know that you have a group and you have a construction of it?
Yeah, well, so before, so historically, the first construction was, which was of course important for everything that followed, was given by Bob Grice. And he constructed a representation. He constructed an algebra on a space of this dimension. And then he managed to choose, well, I mean, okay, he found an algebra structure on a space of this dimension for which the automorphism group is the monster. Which sounds a little bit easier than what he actually did. So because this algebra that he constructed has like no identities. It's commutative but not associative, and that's almost all you can say about it. So it was an amazing feat. But he constructed it as a,
So in this story, where does that fall?
well, so this turns out to be this larger space turns out to be an algebra in a kind of more natural sense, so-called vertex algebra, vertex operator algebra.
Our book describes everything. Vertex operator algebra is an answer.
Right.
And I promise it's readable because we keep using it with graduate students and they can all read it.
And it's the algebra structure here that connects this whole subject to physics and more specifically conformal field theory. Yeah, of course. Yeah. Okay. So Umbral moonshine is a kind of moonshine that involves Mach modular forms. So Umbral moonshine emerged around 2010, involves Mach modular forms. And Mach modular forms emerged around 2000, much kind of sort of in large part due to Zweig's, but like others as well. So invented Mach modular forms, or invented the notion of Mach modular form. In order to give context to the Mach theta functions of Ramanujan. Amazingly, for me, Ramanujan's name has already appeared in today's talks, but I think in a completely unrelated way. And well, these Mach theta functions, so my understanding is that they first come to light in 1920. So, so in his last letter to Hardy, Ramanujan mentions some examples of things he calls Mach theta functions, but doesn't really explain what they are. So here's an example of one of Ramanujan's Mach theta functions. FQ by consider this Q series. Okay, so is the definition clear? So this is some Q series, and it's not a modular form. But for Ramanujan, it was kind of as good. So he had some motivation. So for him, this was a special Q series.
Is it
And
a power series, or does it have some?
Sorry, say again.
What kind of convergence properties like this?
It should be holomorphic on the holomorphic in the upper plane. Yeah. You have enough stuff down. So and we've kind of for decades and decades struggled to kind of understand to come up with a framework that includes these guys in something like the theory of modular forms, and Zweig's arrived at that. So I decided that I would go ahead and try and motivate the notion of Mach modular form in a concrete way. So I'm going to say this is modular, but in a twisted sense. And now I'll try and motivate the twisting. Okay, so it's extremely elementary. So take a group like gamma naught M or something. And let G be a cusp form of weight 2. On gamma, then G gives us an invariant differential on the gives us a holomorphic differential on the curve X gamma.
So what do you notice S2 gamma?
Oh, cusp forms of weight 2. Cusp forms of weight 2 on gamma. Yeah. So if we have a differential on the curve, then we should be able to get a gamma invariant function by if we have a gamma invariant differential, we should get a gamma invariant function by integrating Okay, let's do that. So define f of tau to be the integral from gamma to infinity. I mean, it's in the imaginary part of tau to infinity of gz dz. So is it gamma invariant? So hopefully we get 0. And of course we don't. So this is, so by gamma invariance, we can replace z with gamma inverse z, and this thing stays the same, and we get gamma inverse, we get the integral from gamma inverse infinity to infinity of dpc. So f is not invariant, not gamma invariant. So we failed. Or we succeeded. If actually is gamma invariant, but not for that action that you were thinking of, for the twist of that action by this integral expression. Twisted gamma action f slash twisted by g of gamma. We find that to be f of tau plus integral gamma inverse g c. So classically, this is an abelian integral. Classical language, this is an abelian integral. Modern language, this is a Mach modular form of weight 0. So, and okay, so we'll see how this goes down. So it's a Mach modular form of weight 0, except that it's a convention somehow to introduce a lot of conjugation. So well, let me just write down. So that in general, for general K, for general weight K, the twist is F slash, say the weight K operator twisted by G gamma tau is the usual action plus this integral negative E plus tau minus K. So in general weight, you need to do something to fix the weight, fix the invariance here. And, for reasons I won't go into, this is the convention. Okay, so Mach modular form is a very familiar notion. Or at least it's a natural thing. Okay, so now let's now this thing I'm erasing is a Mach modular form of weight 1/2, essentially, but I'll say something a little bit more concrete in a minute. So I'll try and summarize now what Umbral Moonshine is in a kind of omnibus theorem. There are more names I should put here, but let's do this. So firstly, for each non-fricker genus zero curve of the form x naught m plus n comma m prime. So by here I mean include some more, as many Eck and Lena involutions as you like, but just don't include m itself. It's the non-fricker part. So there's some finite list of possibilities, which is genus zero. For each one, there exists a distinguished Mark modular form. I will denote like so. Of weight 1/2. With integer coefficients. And so, let's think if the curve is kind of further restricted, the curve you chose in one as the form it's simply an x naught m, that's genus zero, or it's x naught m for some m plus m over 2 for some even m, or it's x naught 12 plus 4, or it's x naught 30 plus 6, 10, 15. Then in these cases, these modular forms are actually greater dimensions for module split groups. And the associated modular form is the greater dimension function of a module for a group that I'll call M, this is a G to the funny symbol. And I won't tell you what G is. Yes.
It's a simple group.
Okay, so the reason I'm not telling you right away is that it gives me so in order to have sufficient dramatic build up to the punchline of this part of the talk, which is that a paper of Professor Ogg from 1975, also from 1975, gives us clues as to what these groups are supposed to be.
5 minutes.
5 minutes, okay, great. Okay, so G symbol equals what? Question. So clue. So again, this is Ogg in a different paper from 1975. Okay. The primes P not 2 such that every super singular point of x naught 2 and characteristic characteristic P is FP rational, find of FP are the following: 3, 5, 7, 11, 23. And now I will reveal what gamma 2 is. Gamma 2 is the sporadic simple group M24. Its order is 2 to the 10, 23 times 5 times 7 times 30 times 23. Modulo typos. Okay. So not just gamma, not just x not 2, but the kind of, I mean, this is the Ogg's observation from monstrous moonshine, but for elliptic curves with level structure. This is the you know, consider the analogous question of supersingularity, but for elliptic curves with level structure. And of course, this paper treats other cases. And kind of you see magically these groups are predicted also by this.
They're all related to simple groups, or do you get classical Shabalala?
Yeah, so what happens is these groups actually get pretty small pretty quickly as the level increases. Yeah. So of course, as the level increases, the supersingular points, which can all be rational, you know, blah blah blah, that goes down as well. So you end up kind of running out of primes pretty quickly. Yeah. Okay. How many of my 5 minutes are left? 2. Okay. Okay. Perfect. Perfect. So I just want to. So at this point, right, it's natural to ask. I mean, you see this moonshine business, and it's quite amusing, but it's natural to ask how rich the relationship between finite groups and modular forms really is. And if you're interested in modular forms because you're interested in cusp forms, which would, you know, be a natural thing, then the stories we've described, the story we've described so far is kind of exactly not what you're interested in, because it occurs exactly when the cusp forms don't. Okay, so my personal expectation is that this moonshine story does extend in a meaningful way into the realm of cusp forms and modular forms with rich arithmetic and geometric content. Whether or not you want to call it moonshine is you know, a separate question. Right? In the one of my last 2 remaining minutes, I'll just kind of hopefully try and give you an indication of how Ogg's torsion conjecture is kind of a clue as to how the kind of in support of this. So amazing fact. So there's a mechanism for getting from this Umbral Moonshine for x naught, for the curve x naught 3 to so there's a group, and then there are trace functions attached to it, and to each one we get there's a way of translating this to some hg. I'm just going to even call it h3. So now a Mach modular form. This is a holomorphic Mach modular form of weight 3/2. Okay, and level given by the order of G. And it turns out that at level 1, there's exactly one such thing, which is the generating function for class numbers, for quadratic imaginary class numbers. So, so it turns out that you get a kind of curious interpretation of quadratic imaginary class numbers as dimensions of virtual representations for some. Well, it turns out to be a sporadic group. The group here is double cover of M12. Now, if you look at the in particular the function attached to an element of order 11 here, 11 appears when you take x naught of 3 instead of x naught of 2. Then you get a kind of Eisenstein series part and a cuspidal part. And if I have this funny fraction right here because I've normalized this to have integer coefficients. It's the cusp form. The cusp form and it's an arithmetically interesting thing. And the fact that there's a 5 here means that there must be some congruence between this cusp form and this Eisenstein series. Because this thing has integer coefficients. And what is in this congruence right here? So what is this 5? This 5 is exactly the order of the rational torsion of the Jacobian of x naught 11, which of course is x naught 11, but for a general statement, we should do this. And so once you see this, you can forget about M12 and you can just look at groups of prime order, cyclic groups of prime order, and you can ask if this generalizes, and theorem it does.
Absolutely wonderful talk to finish this wonderful day. I think it's clear that you've got much more to say here. You're here tomorrow. And so I'm having lunch with him. Welcome to join us at the dining hall, and maybe you can explain. There's much more to explain here. Anybody wants to? We'll be meeting at noon in the dining hall, and he's here the whole day tomorrow. So I do want to end it because we do have another seminar. But before we end it, Andrew, maybe you want to say a few words. You can just get up and turn around and address whatever you feel like looking at. And maybe this evening at dinner you can give me a Jack Daniels.
Well, I mean, danger is a few words is one of those concepts.
You're the man. You can
drag me off physically. But well, first of all, I'd to thank the speakers for very nice talks, and for all of you for being here, and to say that I enjoyed the whole thing. So I do have one serious comment for this, and that's that mathematics is fun. And this might seem a little bit paradoxical. And I think I can state that all mathematicians, great and small, most of the time are stuck. Present company except other than that. And so how can it be fun when most of the time you're stuck, you're frustrated, you're not getting anywhere, but of course you have the hope that something will come. And of course, there's also the thing that often the joys you get from mathematics are that it's not something you were involved in, but somebody you don't even know says that they used theory of yours, which was helpful. But of course, you were frustrated and waiting for this to happen. You got no way to expect it. That's one way or another. And I think this meeting, I think at least is proof that mathematics can be fun. Have it for me. Thank you.
I think with that, we'll end it because we have some. And thanks very much for everybody.